Welcome to the lecture on electrophysiology of neurons. Part of it has been discussed in the bachelor, so some students will be familiar with this topic. For others it will be relatively new, but don't worry, we will recap the essentials. There are essentially four key properties of neurons. First of all, they all have a resting membrane potential, which is, by the way, not unique for neurons, as all cells in our body have a resting membrane potential. What is unique of neurons is that the membrane potential can very quickly change, resulting in the generation of action potentials. That is illustrated here on the right. This is the resting membrane potential, typically around -60 to -70 millivolts, and this is an action potential, where the membrane voltage quickly changes to +40 millivolt, returns back to normal with a slight overshoot, and returns to normal here. This duration is typically of the order of milliseconds. And in fact, this was one of the key experiments that were performed by Hodgkin and Huxley in the beginning of the last century. Now, another key property of neurons is that they can propagate the action potential along the axon. And an aspect that is very important as well is that all these processes are energy dependent. That is, they need ATP. And we will see later in the course that there are several clinical conditions where there is a shortage of ATP, and that affects either the generation and or the propagation of action potentials. There's a very large number of neurons in the brain, approximately 100 billion, and each neuron makes, on the average, 1,000 connections. And their key way of communication is through chemical synapses. We will treat those as well shortly, which is very complex to model in detail. That's why in this course we will treat various simplifications with, of course, preservation of some essential components that we think are relevant for the particular discussion at hand. So what will we treat today? We will discuss the Nernst potential, the membrane potential, the Goldman-Hodgkin-Katz equation, the conductances, the voltage-dependent conductances, and eventually this will culminate in the Hodgkin-Huxley formalism. And Hodgkin and Huxley, shown on the right here, are the two scientists that made significant contributions to neuroscience in formulating these equations that essentially capture the voltage dependence of neurons in their generation of action potentials. And for the interested student, the Journal of Physiology in 2012 devoted a whole issue to contributions of Hodgkin and Huxley to neuroscience, including, of course, a discussion of the Hodgkin-Huxley formalism. Let's start with the Nernst potential. This has been treated in previous courses, but we will recap some of the essentials here. It is treated in more detail in the lecture notes. Now let's assume we have a neuron, and for simplicity we've only drawn a circle representing the cell body with typical intraneuronal concentrations of the key ions, which is sodium, potassium, chloride, and large macromolecules with a negative charge, indicated here with A-. And on the outside we have the same ions, but in a very different concentration, so sodium, potassium, chloride, and some anions as well. Now clearly there's a big concentration gradient of the sodium, with a gradient from the outside to the inside, and it's basically reversed for potassium. And for chloride, and notice the minus sign, we also have a relatively large gradient from the outside to the inside, and there's this anions. Also note that there is bulk electroneutrality. If you add all the millimolars here, the sum will be 0, and the same applies for the extracellular solution. So the sum of all concentrations, basically the sum of all particles, must equal 0 in the bulk solution. It might be different, very close to the membrane, but in the bulk solution there is electroneutrality. Now, as you may recall, cell membranes are typically semi-permeable for part of the ions, and that's illustrated here on the right. And the semi-permeability results in the selective semi-permeability results in a particular membrane potential that is essentially dictated by the ratios of the permeabilities of the various ions at hand and their associated Nernst potentials. Now that's illustrated here on the right for part of a cell membrane, where apparently the transmembrane potential is in rest for these ion concentrations between -60 to -75 millivolt. Those are biologically plausible values. And per ion channel for sodium, potassium, and chloride, calcium, the Nernst potentials are indicated here. Values are in millivolts. So you may not recall this in detail, so we will recap some of those aspects that are essential for the generation of the membrane potential and the Nernst. We'll start with a simple system composed of two compartments, one on the left and one on the right, and separated by a semi-permeable membrane that is only permeable for the positively charged ions. Now, to preserve bulk neutrality, we cannot only have positive ions in solution on the left side, so we need to have negatively charged ions as well, and that's indicated by the B minus, and those add to 0, the total number of particles, and these anions cannot cross the membrane. So the membrane is only semi-permeable for the positively charged ions. Now these guys clearly want to diffuse from the left to the right, as the concentration here is assumed to be larger than on the right side. But note that in order for electroneutrality in the bulk solution to be preserved, they will drag along essentially their negatively charged ions when they tend to cross the membrane. And that very quickly results in a situation that is sketched here on the right side. So part of the positively charged ions will cross the membrane and will essentially reside in a very close distance from the membrane on the right side. And at the same time, part of the negatively charged anions here will leave the bulk solution, you could say, and they will reside on the other side of the membrane. So note that we have now charge separation across the membrane, resulting in a voltage difference. There's still electroneutrality in the bulk solution, and there's electroneutrality still on the right side. So what happens is that as a result of both a concentration gradient and a membrane that is semi-permeable, a voltage difference will be set up across the membrane, and that voltage is known as the Nernst potential. And it's the potential where the diffusion current exactly matches the electrical current, where the total net current through the membrane is 0. And this can be expressed in the equation written down here, which is called the Nernst equation for a particular ion, and at 37 degrees Celsius the value is approximately -61.5 logarithm base 10 of the concentration gradient of the ions, and then the value is in millivolts. Now details of the derivation can be found in the lecture notes. So the Nernst potential is a true equilibrium. There's no current, no net current across the membrane, and you can clearly define Nernst potentials for different ions. And that was actually what was shown on the previous slide, and we'll go back to it. On this slide, depending on the concentration gradients of sodium and potassium and chloride and calcium, the Nernst potentials are given here, and those are calculated by the formula I just introduced, by the Nernst equation. Now clearly, in biological reality, we don't have a single ion species of cations and anions only, but there are several. And here it is illustrated for two. For instance, for sodium chloride and potassium chloride. In this case, sodium chloride, for instance, on the inside, potassium chloride on the outside, or vice versa. And depending on the relative permeabilities, there will be more or less charge separation of each individual ion pair. Now, the resulting voltage that eventually occurs in resting conditions is now given by the Goldman-Hodgkin-Katz voltage equation, and that's expressed here. So if you look carefully, it's essentially a modification of the Nernst potential, as this is exactly the same as the Nernst potential, but now we have to deal with different ions, not only, for instance, potassium or only sodium, but a combination of those, and the relative contribution of those ion concentrations to the final membrane potential is dictated by the relative permeabilities. Now clearly, if we had to deal with a membrane that is only permeable for potassium and the permeability for sodium and chloride would be zero, then this equation reduces to the Nernst equation of potassium. And we can simulate it as well with the Goldman-Hodgkin-Katz simulator. So we will illustrate the Nernst potentials of potassium, sodium, and chloride with the Goldman-Hodgkin-Katz simulator, and we will also show how the Goldman-Hodgkin-Katz equation can be used to estimate the resting membrane potential if we have the situation with several ion pairs. Now what is shown here is the Nernst equation at 37 degrees Celsius, and if we have a potassium gradient as illustrated here, then the corresponding Nernst potential is minus 61.5 millivolt. And if we take a physiological concentration gradient of sodium, then we find that the concentration is exactly the gradient, exactly in the opposite position as for potassium, and the corresponding Nernst potential is plus 61.5 millivolt. So this all follows directly from the Nernst equation. And if we would have chloride in this concentration, the Nernst potential associated with this concentration is minus 61.5 millivolt. Notice that the gradient is the same as for sodium, but chloride has a negative charge, so the Z here changes sign, which is why there is minus 61.5 millivolt. Of course, there's a small temperature dependence, but we have the situation at 37 degrees Celsius. If we would look at temperature in general, we can use this expression where the absolute temperature is here indicated. Now, what is the situation with multiple ions? Then we can use the Goldman-Hodgkin-Katz voltage equation expressed here. And then it's not only the concentration gradients of the different ions, but also their individual permeabilities indicated with the P's. Now, in this situation, the permeability, let me go back to a more standard situation. So this is a cell, a generic cell with a permeability of sodium of about 5, potassium 100, and chloride 10. And this results in a resting membrane potential of minus 60.5 millivolt, which is very typical for a generic cell at rest. And actually this is very close to the sodium for the potassium Nernst potential, because in rest the permeability for potassium is much larger than that of sodium. We can change that, of course. For instance, if we could set the sodium permeability to a large value and the potassium permeability to a low value, and then it's clear that the membrane potential tends to be very close to the Nernst potential of sodium. So this illustrates how the membrane potential depends on ion concentration gradients and permeabilities. And to illustrate the concentration gradient, we could have a situation, for instance, if I go back to the generic cell in rest and the concentration gradient of potassium would change. For instance, I change the extracellular concentration of sodium to a ridiculously large value, say 20 millimolar, which is extremely large. So maybe I should put it around 10 or 11, which is still quite large. Then it's clear that it has a tremendous effect on the resting membrane potential, which is one of the reasons why buffering in the body is extremely precise, to keep, in particular, potassium gradient, so the potassium concentration in the extracellular space, very tightly regulated between 3.5 and 4.5 millimolar, because this illustrates the tremendous sensitivity of small changes in the extracellular potassium on the resting membrane potential. And as we will see later, this significantly affects the excitability of neurons, which is why extracellular potassium concentration needs to be regulated in a very narrow bandwidth, a very narrow range. Another way to express the membrane potential is as a weighted sum of Nernst potentials, as illustrated, as indicated with the equation here. So the membrane potential can also be expressed as the conductance of sodium times the Nernst potential of sodium plus the conductance of potassium times the Nernst potential of potassium divided by the sum of the conductances, assuming that in this case we only have to deal with sodium and potassium. So why is that? Well, we can turn our illustration 90 degrees, and then we introduce an electrical equivalence scheme, which was also introduced by Hodgkin and Huxley, by the way. And this schematic essentially illustrates a semi-permeable membrane with two key players, sodium and potassium. Now the battery here represents the Nernst potential of sodium, and this conductance represents the conductance of sodium. And we can make a very similar circuit in parallel for potassium, and note that the battery is in a reversed order because the Nernst potential of potassium is has a different sign than the Nernst potential of sodium in biological conditions, because the concentration gradients are basically inversed. Now, of course, in biological reality, we, well, maybe not of course, but in biological reality, the membrane is also not completely semi-permeable, but non-semi-permeable for multiple ions as well, and that is typically represented by a leak current and a leak Nernst potential. So this is a conductance that is unique for potassium. This is a conductance that's unique for sodium, and we have a leak current that does not differentiate between the two ions. So this is the resistive properties of our cell membrane, and there's one other component we have not indicated yet, and which is the cell membrane capacitance. And if we add that, we arrive at this electrical equivalent circuit, and this is essentially the key, summarizes the key components of the passive cell membrane with the sodium, potassium, and the leak current, and the membrane capacitance. We can now derive an expression for the total current in the circuit that, according to Kirchhoff, needs to be zero, the sum of all currents, and then we arrive at the expression that is given here. notice that it is the capacitive current, which is given by the capacitance times the time derivative of the membrane voltage. And this current must equal all these currents. Now, if we would look at the equilibrium situation where there's no change in membrane voltage, so the membrane voltage is at rest, then the capacitive current is zero, and then we arrive at this expression. So the membrane voltage, and actually we've seen this already, is basically a weighted sum of the Nernst potentials that are weighted by the conductances. And this is the voltage that is present in a neuron when there are no changes in the current, when the membrane is at rest. And in the next part, we will discuss how action potentials will be generated, because the interesting part of neurons is that the conductances, in particular of sodium and potassium, are not constant, but they are a function of the membrane voltage. And that gives rise to very non-trivial dynamics and also makes the generation of action potentials possible. So that will be discussed next.